Hello everyone, this is a video lesson on an introduction to torque, and I would recommend that you take some notes in your physics notes. What we're going to do in this video is introduce the definition of torque and show how you can calculate the torque on an object. So this is kind of our beginning of learning about rotation, and torque is actually the thing that causes objects to rotate. And we're going to start off by saying that. So torque causes rotation. And so think about this as an example. If you think about opening up a door, you grab the doorknob and then you have to pull on the door. So obviously it takes a force to cause something to rotate because the door has to swing open. It has to rotate around its hinge. But it also takes more than just a force. You have to actually apply the force in a certain way to cause the door to open or close. And so that's something that makes torque unique. So torque causes rotation, and we're going to say that it is the product of two things. It's the product of force and what we call lever arm, which is a distance. So I think maybe to illustrate this, let me just make a sketch, and I'm going to draw, okay, how about a door? And so this doesn't look like a door, but if you were to see a door from up above, the hinge would be at one end. So we're going to call that the pivot. So this is the hinge part of the door, and this is the actual body of the door. Okay. And the idea would be that when you want to pull the door open, you might apply a force this way. Okay, so we're looking at the door from above, right? And you would apply the force this way, and that would cause the door to kind of swing and rotate that way. Okay? Now, one of the key things here is that in order for that to happen, is you want your force to be far away from the pivot. This is why they place doorknobs at the opposite end of the hinge. And so the distance between the pivot and where you put the force, that's what's called the lever arm. And so the lever arm is the distance from pivot to point at which force is applied. And I'll tell you, it's really, you need to have these two things together to cause the door to open successfully. All right. If you've ever tried to open up a door by pulling at a point which is very close to the hinge, you know it's really hard. It's probably easier to try to push it open. So next time, go up to the door in your room and try to swing it open by applying the force really close to the hinge. It's very hard to do because you just don't get much torque out of that. So the way that you get a lot of torque is by taking your force and you pull it way, way, way out, and you put it as far as possible from the pivot. This is really the idea behind a lot of common tools. If you think about a wrench, right? There's a wrench, and then the idea would be that you apply the force out here, and you're making this distance, we'll call that R. You make that distance really big, and that gives you a lot of torque because you're making both of these things big. And then your pivot, I'll put a P there, or a circle. The pivot is going to be wherever the bolt is. Okay? So a lot of tools work this way because you have a handle which is very long, and that gives you a long lever arm. Okay. Let's look at the kind of the calculating part of this. And we'll take some examples here. Let's think about meter sticks. And I'm going to draw 3 lines. And these are going to be like the meter sticks that we used in our lab. I'm going to put a P for a pivot right in the middle. And then what we're going to do is we're going to look at what happens if you apply a force in different locations. Okay? So let's do the first one here. Let's say that I apply a force here of 100 newtons, which is quite a bit. And so this is a meter stick, so the distance is going to be 1/2 meter, right, from the center of the meter stick out to the edge. Okay? And the effect of that force acting at that lever arm is going to be to cause rotation that goes in that direction. Guys, we're going to say that when the meter stick rotates in this direction, it's rotating in the same direction as the hands of a clock. So this is going to be a clockwise rotation. Okay. How much torque do we get from that? Well, we would get basically the product of these two things. We would get 100 newtons multiplied by 1/2 meter, and that's going to give us 50 newtons times meters. So that number 50 is giving me a sense of how much torque I'm getting, all right? And I need to know the force and I need to know the distance. Okay. Let's compare that to a different situation. Let's say that I take the same force of 100 newtons, but I move it in. So now I'm only at 1/4 of a meter. So this would be like taking a doorknob and moving it closer to the hinge. The effect is going to be you're going to get less torque. And you can say exactly how much less by calculating the product of 100 newtons times 1/4 of a meter. And now I'm only getting 25 newton meters. So I really have half as much torque. Why? Because I shortened the distance of the handle of the lever by a factor of 1/2. Also, you'll see in this case about direction, this would also be a clockwise direction. Let's do one more example, and in the last example, why don't we put the force over on the other side, and this time I'm only going to put 50 newtons out, apply 50 newtons. This is on the opposite side of the meter stick, and now my distance will be 1/2 meter going that way. This will also give me a torque, but there will be several differences. Number one, the direction is now going to be CCW, which means counter clockwise. So I know we all love digital, our phones and things like that, but you have to know the difference between clockwise and counterclockwise from these pictures. So please get familiar with that. Let's look at the actual size of that torque. Here we would have 50 newtons multiplied by 1/2 meter, and that gives us 50 times 1/2 is 25 newton meters, which happens to be equal to the other torque. So, you know, it's basically the same strength of a torque, but it's in a different direction. And so you have to always look at torque, and the most important thing with torque is you have to know where is the pivot. Okay, so pivot is everything. Very important. Without a pivot, you really can't say anything about torque. You have to have a pivot in mind when you calculate torque. Okay, so let's sum this up. Torque is a product of force and lever arm. I'm going to put down a formula. I'm going to write down units, and then we're going to talk about direction, because we've now seen how this works, so it's just a matter of connecting a few things to it. So the formula for torque that we're going to use is going to be this. Okay, so I'm going to use the symbol here for torque, which is the Greek tau symbol. It's an uppercase T, T-A-U. It's called a tau. And the tau is a vector because torque has a direction. We'll talk about that in a minute. But the torque is going to be equal to the product of the force times that lever arm, okay, that we've talked about in these pictures and identified in the pictures. So you multiply those two things together, that tells you what your tau is going to be. So by multiplying 100 times a half, we get 50, or 100 times a quarter, we get 25. That's what we're doing when we multiply here. Now, for units, we've already seen the units are going to be meters times newtons. Oftentimes, this is just written Newton meters. It doesn't matter, right, what order you put those in. And I'm just going to say here for now that these are not joules. Remember, when we did joules, we said joules was work is equal to force times distance, and so we would have newtons times meters. Well, you might think that torque is in joules. It's not. And the reason, the really short answer to that is because when you talk about torque, the newtons and the meters are always at a right angle to each other. Okay, they're always perpendicular. When we talked about joules, newtons and meters were in the same direction. So that's the difference. So we could talk more about that in class, but these are not joules. And finally, for direction, the options are going to be clockwise or counterclockwise. And that's because torque is a vector. And it's a different type of a vector. It's a rotational vector. Okay? Maybe we should say that. I'm going to add the word rotational. And so we don't talk about up or down or left or right. We talk about clockwise or counterclockwise. So you're going to have to get used to that in this unit because we're now going to talk about objects rotating, and the direction of rotation is very important. And you're always going to talk about either clockwise or counterclockwise when you're specifying that direction. Okay, so that kind of concludes our lesson here, and we'll talk soon.